There is no urgent thing that needs to be done at this hour. The world has shifted into its quieter tones, and so can you take one slow breath now and another and let yourself begin to drift. We are going to drift very slowly into the quiet, rust-colored world of Mars, the red planet of the inner solar system with its vast cold deserts of iron, the tallest mountain known to science, the deepest canyon in the solar system, and the patient stillness of an entire planet that may once have held oceans. This is the Circadian Institute, a place for slow stories at the edge of sleep. We do not raise our voice. We do not ask anything of you. We simply travel together, somewhere quiet until rest finds you. Tonight we are visiting the deep, slow story of Mars, the fourth planet from the Sun, with its red, iron-rich surface, its thin pink atmosphere, the enormous shield volcano of Olympus Mons rising 26 kilometers above the plains, the great rift canyon of Valles Marineris stretching 4,000 kilometers across the planet, the two tiny moons Phobos and Deimos, the polar caps of frozen water and carbon dioxide, the ancient riverbeds and lake floors that hint at a wetter past, and the quiet, patient search for any sign of life that may once have existed there. Subscribing helps these nightly journeys keep going. Tonight, we will travel together through the world of Mars. We will visit the red iron-rich surface of the planet itself, the enormous volcano of Olympus Mons, the great canyon of Valles Marineris, the polar caps of frozen water and carbon dioxide, the small moons Phobos and Deimos, and the patient quiet search for any sign of life that may have once existed there. There is no hurry. We have all the time we need. To begin tonight's journey, we will visit Mars itself. Mars is the fourth planet from the Sun and the second smallest planet in our solar system. Only Mercury is smaller. Mars is about half the diameter of Earth, with a surface area roughly equal to all the dry land on our planet combined. Despite its smaller size, Mars is a world of enormous geological features and quiet ancient history. Mars orbits the Sun at an average distance of about 228 million kilometers. That is roughly 1.5 times the distance from Earth to the Sun. Light from the Sun takes about 13 minutes to reach Mars. The Sun, seen from Mars, would appear about 2/3 the size it does from Earth, and the daytime sky would be a soft butterscotch pink rather than blue. A single Mars year, the time it takes Mars to complete one orbit around the Sun, lasts about 687 Earth days, nearly 2 Earth years. A person living on Mars would celebrate a birthday roughly half as often as a person living on Earth. The long Mars year gives the planet long, slow seasons, each lasting several Earth months. Despite the long year, a single Mars day lasts only 24 hours and 37 minutes, remarkably close to an Earth day. A traveler from Earth would find the Martian sense of time almost familiar. The day is called a sol, and it is the basic unit by which all Mars rover missions plan their work. A rover's life is measured in sols. Mars is about half the size of Earth in diameter and about 1/10 of its mass. The surface gravity on Mars is roughly 38% of Earth's. A person who weighed 70 kilograms on Earth would weigh just 26 kilograms on Mars. A simple step would lift a Martian explorer high into the thin pink sky. The rust-red color of Mars comes from iron oxide, common rust, that coats the planet's surface in a fine dust. Billions of years ago, when Mars had a thicker atmosphere and liquid water, the iron in its rocks reacted slowly with oxygen and water to form this layer of red iron oxide. Today, the planet remains red not because it is rusting now, but because the rust from long ago has never been washed away. Mars has been visible to human eyes throughout all of recorded history. Because of its red color, the planet has been associated with blood, fire, and war in cultures around the world. The Romans named it after their god of war, Mars. The Babylonians called it Nergal. The Egyptians called it Her-Desher, the Red One. The ancient Chinese called it the Fire Star. Mars has shone steadily in the night sky as humans built and rebuilt their civilizations beneath it. Mars was first observed through a telescope by the Italian astronomer Galileo Galilei in 1610, the same year he first observed Saturn. The first detailed maps of Mars were drawn in the 1800s, when astronomers thought they could see straight lines they called canals on the surface. The lines turned out to be optical illusions, but the dream of life on Mars had taken hold and has shaped human imagination ever since. The mass of Mars is about 1/10 that of Earth. Like all the inner planets, Mars is a rocky world with a solid surface, an iron core, and a thin atmosphere. Unlike Earth, Mars has no global magnetic field today. Long ago it did, but the planet's small size allowed its inner core to cool faster than Earth's. With the dynamo stopped, the global magnetic shield faded, leaving the atmosphere exposed to the solar wind. Deep beneath the surface of Mars, the iron core is small compared to Earth's. The core measures perhaps 1,800 kilometers across, about half the diameter of the planet itself. The core is partially liquid, with a solid inner part wrapped in a deeper outer molten layer. The slow cooling of this core long ago is one reason Mars no longer generates the magnetic field that once protected it. The surface temperature of Mars is very cold. At its average, the surface is about -60 degrees Celsius, colder than the coldest place on Earth. In summer, near the equator, the daytime temperature can briefly rise above freezing. In winter, near the poles, the temperature plunges below -125 degrees Celsius. The thin atmosphere holds very little heat, and the temperature can swing wildly between day and night. The orbit of Mars is more elliptical than the orbit of Earth. At its closest approach to the Sun, Mars receives about 40% more sunlight than at its farthest. This stretched orbit gives Mars stronger seasonal differences than Earth and contributes to the planet's famous global dust storms. The summer in one hemisphere is much warmer than the summer in the other. Mars has been visited by human spacecraft many times. The first successful mission was Mariner 4, which flew past Mars in 1965. Since then, more than 24 spacecraft have arrived. Some entered orbit, some landed. A few have rolled across the red surface as rovers. From these missions, we have learned almost everything we now know about Mars. From Earth, Mars can usually be seen with the unaided eye on most clear nights. It is bright when close to Earth and dim when on the far side of the Sun. Through even a small telescope, the polar ice caps and the major dark patches on its surface become visible. The bright red color makes Mars one of the most recognizable objects in the night sky. Today, Mars is the most thoroughly studied planet beyond Earth. We have detailed global maps. We have rovers exploring its surface. We have orbiters watching its weather. We are searching its rocks for signs of ancient life. We are quietly assembling the knowledge we will need if humans ever travel there ourselves. Mars has become, in a real sense, our second home in the imagination of our species. Tonight, Mars continues its slow journey around the Sun. The red dust drifts across its empty plains. The polar caps slowly grow and shrink. The two small moons trace their patient orbits. Mars has been doing this for 4.5 billion years, since the early formation of the solar system. It will continue for billions more, long after every memory of human civilization has faded. Now, gently, we will look more closely at the thin pink atmosphere of Mars, the soft butterscotch sky that hangs over the red plains. The atmosphere of Mars is very thin. The pressure at the surface is less than 1% of Earth's atmospheric pressure. If a person were to stand unprotected on Mars, the air would be far too thin to breathe, and the lack of pressure would quickly damage the body. The atmosphere of Mars is closer to the vacuum of space than to the rich air of Earth. Despite its thinness, Mars does have a real atmosphere, and that atmosphere has weather. The dominant gas is carbon dioxide, which makes up about 95% of the Martian air. Smaller amounts of nitrogen, argon, and oxygen complete the mix. Water vapor is present in trace amounts. The composition is very different from the nitrogen-rich, oxygen-rich air of Earth. The sky of Mars is a soft butterscotch pink during the day. The color comes from fine red dust suspended in the air. Sunlight passing through this dust takes on the warm rust-pink hue that has become familiar from photographs taken by rovers on the surface. The pink sky is one of the most strangely beautiful sights revealed by Mars exploration. At sunset on Mars, the sky takes on a different and very strange color. As sunlight passes through more dust at the horizon, the blue light scatters less and reaches the surface more directly. The Martian sunset appears blue, in soft contrast to the pink daytime sky. Earth's sunsets are red and skies are blue. Mars is the opposite. The thin atmosphere has very little ability to hold heat. As the sun sets, the surface of Mars rapidly cools. A summer afternoon temperature near the equator can drop from 20 degrees Celsius to minus 70 degrees Celsius within a single Martian night. The wide swing makes the Martian environment one of the most thermally restless in the inner solar system. Winds on Mars can blow at high speeds during major dust storms. Winds can reach over 100 kilometers per hour at the surface. Because the air is so thin, however, those winds have far less force than equivalent winds on Earth. Standing in a Martian dust storm would feel like a steady breeze, even though the wind speeds would be hurricane force. The thin air carries fine particles of red dust across the entire planet. Even on calm days, the lower atmosphere contains a steady haze of suspended dust. This dust gives Mars its overall reddish-pink appearance from orbit and contributes to the colors of the sky at all times of day. The dust is always there, slowly settling and being picked up again. Clouds occasionally form in the upper atmosphere of Mars. These clouds are made of water ice crystals and form at altitudes far above the surface. They appear as faint white wisps in the pink sky and are particularly common over high volcanic peaks like Olympus Mons. The clouds are thin and delicate, drifting slowly across the planet's cold upper air. In winter, in the polar regions, the atmosphere itself can freeze. The carbon dioxide gas that makes up most of the air condenses directly onto the surface as a layer of dry ice. This frozen carbon dioxide sublimates back into gas during the spring, causing seasonal changes in the planet's atmospheric pressure that can vary by as much as 30%. Mars sometimes experiences enormous global dust storms that engulf the entire planet. These storms can last for weeks or months, completely obscuring the surface from orbital cameras. The storm of 1971 was photographed by Mariner 9 and inspired the dust storm chapters of much science fiction. The most recent global storm occurred in 2018 and ended the long mission of the Opportunity rover. Lightning may occur in Mars's dust storms. Friction among the suspended dust particles can build up electrical charges, similar to the way lightning forms in dust devils on Earth. Mars rovers have detected indirect signs of electrical activity in the atmosphere. The thin air means lightning bolts on Mars, if they occur, would be much weaker than on Earth. The thin atmosphere offers very little protection from harmful radiation from the sun. Cosmic rays and ultraviolet light reach the Martian surface much more strongly than they reach the surface of Earth. Any future human settlers will need substantial shielding against radiation. Robotic rovers can tolerate the radiation more easily, though even they are slowly damaged over time. Long ago, Mars had a much thicker atmosphere. The evidence for this comes from the planet's geology. Rivers, lakes, and shorelines that could only have formed with liquid water on the surface, which requires sufficient pressure to keep water from boiling. Over billions of years, the lack of a magnetic field allowed the solar wind to slowly strip away most of the atmosphere into space. Even today, Mars is still losing atmosphere slowly. The MAVEN spacecraft, in orbit since 2014, has measured the present-day rate of atmospheric loss. About 2 to 3 kilograms of atmosphere escape into space every second. Over millions of years, this slow leak continues to thin the planet's air, even as the sun grows hotter and conditions on Mars continue to change. The temperature of Mars's atmosphere varies dramatically with altitude. Near the surface, the air is coldest. Higher up in the middle layers, temperatures actually rise slightly. The thermosphere at the top of the atmosphere can reach hundreds of degrees in the daytime due to solar heating, even though the air there is extremely thin. The structure of the atmosphere is layered and complex. Tonight, the thin atmosphere of Mars continues to move quietly across the red planet. Dust drifts slowly across the plains. Frost forms in the cold shadows. Wispy ice clouds gather above the volcanoes. The Martian sky remains its butterscotch pink, fading to deep blue at sunset, brushed with the soft light of distant stars at night. Now gently, we will descend through that thin sky and look at the red surface of Mars itself, at the rust-colored, iron-rich plains that cover almost the entire planet. The surface of Mars is covered almost everywhere by a fine layer of rust-red dust. The dust is mainly iron oxide with smaller amounts of silica and other minerals. Beneath the dust lies a rocky regolith of broken stones and pebbles. Underneath that is the solid bedrock of the Martian crust. The red dust on top is only a few centimeters thick in most places, but defines the entire color of the planet. The iron in the Martian dust comes from the planet's volcanic rocks, which contain a high proportion of iron-rich minerals. Long ago, when Mars had liquid water and a thicker atmosphere with more oxygen, this iron slowly reacted with water and air to form rust. The rust accumulated as fine dust over billions of years. Today, the surface is uniformly red because the rust has nowhere to go. The texture of the Martian surface varies from place to place. In some regions, there are smooth plains covered in fine dust. In others, there are rocky terrains scattered with boulders. The southern hemisphere is generally older and more heavily cratered. The northern hemisphere is younger, smoother, and lower in elevation. The boundary between these two regions is one of the most distinct features in the solar system. Craters are common across the Martian surface. Some craters are very old, dating back nearly 4 billion years. The largest crater on Mars, called Hellas Basin, is about 2,300 kilometers across, larger than the longest distance across the continental United States. The basin floor lies 7 kilometers below the surrounding plains, making it the deepest known crater in the solar system. The dust on Mars is exceptionally fine, finer than the dust found in most places on Earth. The particles are about the size of those in cigarette smoke. The fine grain size allows the dust to be lifted easily by Martian winds and to remain suspended in the air for long periods. It also allows the dust to coat solar panels on Mars rovers, gradually reducing their power until winds clean them again. Rocks scattered across the surface come in many different colors and shapes. Most are dark gray or black volcanic rock, basalt, that has been partially coated in red iron dust. Some are sedimentary rocks that may have formed in ancient lake beds. Others are meteorites that fell from space. The rover missions have cataloged thousands of different rocks, many of which suggest a wetter and more active past. Sand dunes are common on Mars. Some are small and shifting, sculpted by daily winds. Others are vast fields of dunes covering hundreds of square kilometers, with crests and troughs that slowly migrate across the surface over centuries. The dunes are made not of silica sand like Earth deserts, but of fine basaltic and iron oxide material. They are red and dark, depending on where exactly the dust has gathered. Dust devils, small whirlwinds, are common across the Martian plains. A dust devil is a vertical column of rotating air that picks up loose dust as it moves. They can rise hundreds of meters or even kilometers into the air. Rover cameras have caught many dust devils on video moving slowly across the surface. They are a familiar feature of Martian weather and remind explorers of similar whirlwinds in Earth's deserts. Beneath the loose dust, the regolith, the layer of broken rock and soil, extends downward for many meters in most places. Below that, the bedrock is composed mostly of volcanic basalt, sometimes layered with sedimentary deposits where ancient water once flowed. The Mars rovers have drilled small holes into this surface to study what lies beneath the topmost layer of dust, finding rocks with telling chemistry. The composition of Martian rocks differs from Earth in some interesting ways. Mars has a higher proportion of iron and sulfur on its surface than Earth does. The crust is also rich in olivine, a green volcanic mineral. The most common bright rocks are forms of iron oxide and iron sulfate. Together, these minerals tell a story of ancient water and volcanic activity that shaped the planet long ago. Mars has very weak weathering compared to Earth. With almost no liquid water and a thin atmosphere, rocks erode very slowly. Wind and dust are the main forces shaping the surface today. As a result, very ancient features remain remarkably well preserved. Some of the rocks photographed by Mars rovers are more than 4 billion years old and look almost as they did when they first formed. Permafrost, permanently frozen ground, lies beneath the surface across much of Mars. The shallow subsurface contains layers of water ice mixed with rock and dust. In some places, ice is visible at the surface, especially after fresh impacts have excavated buried ice. The Phoenix lander discovered water ice just a few centimeters below the surface in 2008. In some areas, the surface shows the strange patterns of polygonal terrain. These are roughly hexagonal cracks in the ground, sometimes meters across, that form when buried ice expands and contracts with seasonal temperature changes. They look much like the polygonal terrains found in Arctic permafrost on Earth and are evidence of recent freeze-thaw cycles in the Martian subsurface. The colors of Mars, when seen up close from rovers, are not uniform. There are tans, oranges, browns, and even some yellows and dark grays. Different regions reflect light differently depending on the local rocks and dust. Curiosity rover photographs from inside Gale Crater show layered hillsides in soft pastels of red, tan, and gray. The variations tell scientists about the differing histories of each location. Tonight, the red surface of Mars lies quiet under the thin pink sky. Dust drifts slowly across the plains. Sand dunes hold their long parallel forms. Rocks rest where they have rested for hundreds of millions of years. The silent landscape stretches on and on across the cold, rusty world. Now, gently, we will rise from the plains and visit one of the most extraordinary features in the entire solar system, Olympus Mons, the tallest volcano known to science. Olympus Mons is the tallest known volcano in the solar system. It rises about 26 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest above sea level. Its base measures more than 600 kilometers across, larger than the entire state of Arizona. If placed on Earth, Olympus Mons would tower above almost every feature on the planet. Olympus Mons is a shield volcano, a broad, gently sloped mountain built up over hundreds of millions of years by repeated flows of slow, runny lava. Unlike the steep, cone-shaped volcanoes of Earth, Olympus Mons rises in long, gentle slopes that look almost flat to the human eye standing on them. The average slope angle is only about 5 degrees. The reason Mars can support such an enormous volcano is its lack of plate tectonics. On Earth, the crust is broken into plates that slowly move. A volcano sits on a hot spot in the mantle, but as the plate above moves, the volcano is carried away from the heat source and a new one grows. This is how the Hawaiian island chain formed. On Mars, The crust does not move, so a single volcano can grow for hundreds of millions of years over the same hotspot. The summit of Olympus Mons contains a complex caldera, a large bowl-shaped depression formed when the volcanic magma chamber beneath it collapsed after eruptions. The caldera measures about 80 kilometers across and consists of several overlapping circular depressions, each formed in a different collapse event. The walls of the caldera drop several kilometers down to its flat floor. Around the base of Olympus Mons lies a steep cliff several kilometers tall. This basal scarp is one of the most distinctive features of the volcano. The cause of the scarp is still debated. It may be the result of glacial erosion, mass wasting, or volcanic flow boundaries. From the surface, the scarp would appear as an enormous vertical wall extending up into the sky. Olympus Mons last erupted relatively recently in geological terms. The most recent lava flows on its slopes appear to be less than a few 100 million years old, and possibly much younger. It is not impossible that Olympus Mons may erupt again in the future, though the chance of this happening soon is very small. The volcano may simply be in a long, quiet phase. The volcano is part of a larger volcanic region called Tharsis, which contains the 4 largest volcanoes on Mars. Olympus Mons sits at the edge of the Tharsis region, with the other 3 giant volcanoes, Ascraeus Mons, Pavonis Mons, and Arzia Mons, lined up to its southeast. Together they form a vast volcanic complex unlike anything else in the inner solar system. Because of its great height, the summit of Olympus Mons extends above most of the thin Martian atmosphere. At its peak, the atmospheric pressure is less than a tenth of what it is at the planet's average surface. Standing at the top, a future explorer would look down through almost no air at all, and the sky above would appear nearly black with stars visible during the day. From orbit, Olympus Mons appears almost circular, with subtle radial patterns of dark lava flows running down its slopes. Earlier observations from telescopes had identified a bright spot on Mars and named it Nix Olympica, the snows of Olympus, because of its tendency to appear bright when capped with water ice clouds. When orbiters arrived, the snow turned out to be the great volcano itself. The volume of Olympus Mons is enormous, roughly 100 times that of Mauna Loa, the largest volcano on Earth. Over the hundreds of millions of years of its growth, vast amounts of magma erupted from the depths of Mars onto its surface. The mountain is, in a sense, a slow expression of the heat that once flowed through the deep interior of the planet. The slopes of Olympus Mons show many features formed by flowing lava. Long ridges, terraces, and channels where molten rock once moved downhill. Even today, 4 billion years after some of the earliest eruptions, the patterns remain clearly visible. The slow Martian erosion means that even the very oldest features look fresh from orbit. In some places on the volcano's slopes, satellite images show what appear to be ancient glaciers covered by debris. These rocky glaciers may contain large amounts of water ice mixed with rubble. They flowed slowly downhill long ago, carving channels and building moraines that can still be seen today. The presence of glaciers suggests the volcano may have had cold, wet phases as well as hot, dry ones. If a human explorer were to climb Olympus Mons, the slopes would be so gentle that the journey would not feel like a steep climb at all. It would feel like walking across an enormous, gently rising plain. The slopes are so wide that from any point on them, the horizon of the volcano itself would appear flat. Only from a great distance can the full shape of the mountain be perceived. Olympus Mons stands as a quiet monument to the slow patience of geological time. Its rocks formed across hundreds of millions of years of gentle eruptions. Its current shape is the result of forces that operated through eras far longer than the entire span of life on Earth. The volcano has been waiting silently for the next visitor, robotic or human, to climb its slopes. Tonight, Olympus Mons stands quiet beneath the pink Martian sky. The wind drifts gently across its summit caldera. The shadows lengthen across its enormous slopes as the day wears on. Phobos crosses above. The volcano has been standing this way for hundreds of millions of years, and it will stand this way for hundreds of millions more. Now gently, we will travel from this lone giant to the wider volcanic region of Tharsis, the broad elevated land where Olympus Mons and 3 more enormous volcanoes rise above the Martian plains. The Tharsis region is a vast volcanic plateau on the western hemisphere of Mars. It covers about a quarter of the entire planet and rises an average of 7 kilometers above the surrounding plains. The Tharsis Bulge is one of the largest geological features in the solar system and contains the 4 largest volcanoes on Mars, including Olympus Mons. 3 of the Tharsis volcanoes are lined up in a near-perfect row that stretches over 1,500 kilometers. From south to north, they are Arzia Mons, Pavonis Mons, and Ascraeus Mons. Each is a massive shield volcano, rising 12 to 14 kilometers above the plateau. From orbit, the row resembles a string of giant beads laid across the red surface. Olympus Mons sits to the northwest of the 3 lined-up volcanoes, slightly separated from the main row. It is by far the tallest of all the Tharsis volcanoes, taller than Ascraeus Mons by about 12 kilometers. Together, the 4 giants make Tharsis one of the most volcanic places in the inner solar system, possibly the most volcanic place ever. The weight of all this piled lava deformed the entire planet. The crust beneath Tharsis was pushed down, and the crust on the opposite side of Mars was pushed up. The orientation of the planet's axis also shifted slightly to accommodate the new mass. The growth of Tharsis literally tilted Mars. Its long-term effects can still be detected in measurements of the planet's spin. To the south of Tharsis lies a 5th large volcano, Alba Mons. Alba Mons is unusual. Instead of being tall and steep, it is enormously wide and shallow. Its base spans some 2,000 kilometers across, making it the largest volcano by surface area in the solar system. Its slopes are so gentle that they would be barely perceptible to a walker on its surface. The Tharsis Bulge began forming early in Mars's history, perhaps about 3.7 billion years ago. The bulk of the volcanism continued for hundreds of millions of years. Some of the youngest lava flows on Tharsis date to less than 100 million years ago, geologically recent. This suggests that volcanism on Mars may not yet be completely finished, only deeply quiet. The eruptions that built Tharsis released huge quantities of gas into the Martian atmosphere. Water vapor, carbon dioxide, sulfur dioxide, and chlorine compounds all poured out from the volcanoes over millions of years. These gases would have temporarily thickened the atmosphere and warmed the planet, possibly allowing liquid water to exist on the surface for extended periods of time. To the east of Tharsis stretches the Great Canyon system of Valles Marineris, which we will visit next. Some geologists believe the formation of Tharsis caused the rifts and cracks that gave rise to Valles Marineris. The two regions are linked in time and in tectonic origin, twin features born from the same slow shifting of the Martian crust. The lava flows that emerged from Tharsis volcanoes spread out for hundreds of kilometers in all directions. Some flows can be traced almost 2,000 kilometers from their source volcano. The lava was very runny and traveled enormous distances before solidifying. The result is a vast surface of layered basalt that covers most of the eastern half of Tharsis. Tharsis is also the site of some of the strangest volcanic features in the solar system. Long collapsed tubes, lava channels with collapsed roofs, extend across parts of the plateau. Some of these tubes are large enough to walk through, with diameters of dozens of meters. They may eventually serve as natural shelters for future human explorers, protected from radiation and from extreme temperatures by the rock above. Around the edges of the Tharsis Bulge, the Martian crust shows extensive systems of fractures. These cracks formed as the rising volcanic mass stretched and broke the rock around it. Some of the fractures are hundreds of kilometers long and a few kilometers deep. They form a roughly radial pattern like cracks in the rind of a fruit pressed from inside. If a future human visitor were to stand at the foot of one of the Tharsis volcanoes, the slopes would be so gentle and the volcanoes so wide that they would barely register as mountains at all. Only from above, from orbit, or from a high-flying drone does the true scale of the Tharsis volcanoes become clear. From below, they simply blend into the horizon. The Tharsis region likely formed because Mars never developed plate tectonics. On Earth, hot mantle plumes are gradually moved away from their volcanoes as plates shift. On Mars, the crust stays still. A single hot region of the mantle can keep feeding volcanoes for billions of years, and an enormous mass of lava can accumulate above. The result is geological features unlike any on Earth. Tharsis sits as a quiet, sleeping giant. The volcanoes have not erupted in many millions of years, but the deep heat that built them may still simmer slowly beneath the surface. The region remains a fascinating subject for science and a possible target for future exploration, where scientists may one day search for warm subsurface habitat. Tonight, the Tharsis volcanoes sit quiet in the cold Martian night. Their long shadows reach across the red plains. Frost gathers in their caldera floors. The patient mass of the bulge presses gently down on the planet beneath it, exactly as it has for billions of years. Now gently, we will travel from these giant volcanoes to one of the deepest and longest canyons in the solar system, Valles Marineris, the great rift that stretches across the Martian surface. Valles Marineris is one of the largest canyon systems in the solar system. It stretches more than 4,000 kilometers across the equatorial region of Mars, roughly the distance from New York to Los Angeles. In some places, it is 200 kilometers wide and 7 kilometers deep. If it were placed on Earth, it would span the entire continental United States. The canyon was named for the Mariner 9 spacecraft, which discovered it in 1971. Until that mission, no one knew that Mars had such an enormous feature. As Mariner 9's cameras revealed the canyon for the first time, the geology of the entire planet had to be rewritten. Valles Marineris became one of the most studied features in the solar system. The canyon system is not really a single canyon, but a connected complex of parallel chasms, branching valleys and side canyons. The main canyon in the middle is the deepest. To the west are smaller canyon systems that connect to the main one. To the east, the canyon opens into a vast, chaotic region of broken terrain where ancient floods may once have poured out. The depth of Valles Marineris in places exceeds 7 kilometers. To put that in perspective, the Grand Canyon on Earth is about 1.5 kilometers deep at its deepest. Valles Marineris is 5 times deeper, 10 times longer, and 20 times wider than the Grand Canyon. If you were to stand on the canyon floor, the walls above would rise to truly enormous heights. Unlike the Grand Canyon, which was carved by a river, Valles Marineris was probably formed by tectonic activity. As the Tharsis Bulge grew on the other side of the planet, the Martian crust stretched and cracked. The cracks opened into great rift valleys, and over time those valleys were enlarged by landslides, erosion, and possibly the catastrophic release of underground water. The walls of the canyon show layered rocks of many different colors and ages. From the air, the layers form complex banded patterns of red, brown, tan, and gray. Each layer represents a different epoch in Martian geological history. Studying the wall layers is one of the best ways to read the deep past of the planet, like reading the pages of an enormous geological book. Many parts of the canyon walls have collapsed in massive landslides. Some of these landslides are enormous. Single slides cover thousands of square kilometers and reach hundreds of meters thick. Some of the largest landslides in the solar system have happened inside Valles Marineris, sending vast quantities of rock tumbling down to the canyon floor. At the eastern end of Valles Marineris, the canyon opens into a region called chaos terrain. This is a broad area where the surface appears to have collapsed downward into a jumble of mesas, hills, and depressions. Chaos terrain is thought to have formed when buried ice or water-saturated rock suddenly drained away, leaving the overlying surface to fall and break apart. From chaos terrain, several enormous outflow channels run northward toward the lowlands of Mars. These channels appear to have been carved by floods of unimaginable scale, perhaps 1,000 times larger than the largest floods ever recorded on Earth. The flow rates would have been billions of cubic meters per second, lasting only a few days, but moving more water than the present-day Mississippi River carries in a year. The temperature inside Valles Marineris is slightly warmer than the surrounding plains because it is several kilometers below the average surface. The deeper air is also slightly thicker than the surface air on the plains. Some scientists have wondered whether the floor of the canyon might be one of the more habitable spots on Mars for future human explorers, but also possibly for life. Clouds often form along the canyon walls in the early morning. Water vapor in the thin Martian air condenses into wispy ice crystals as cold morning air settles at the bottom of the canyon. Photographs from orbiters sometimes show long lines of bright fog stretching for hundreds of kilometers along the canyon's length, lit by the rising sun. The canyon may once have held standing water, Layered sedimentary deposits on the canyon floor suggest that lakes existed there at various times in Martian history. Some of these lakes may have lasted thousands of years. Their dried remnants are preserved as thick stacks of fine layered rock, faithfully recording the ancient passage of water through this vast Martian rift. Mars Reconnaissance Orbiter has photographed every part of Valles Marineris in extraordinary detail. The HiRISE camera, the highest resolution camera ever sent to another planet, has captured features less than a meter across along the canyon's vast length. The geologists studying these photos have mapped the canyon's history in fine detail, identifying landslides, faults, sediment layers, and possible water ice deposits. Valles Marineris is among the most likely candidates for early human exploration of Mars. The relatively higher pressure at the canyon floor, the protection from radiation provided by the towering walls, the geological treasures in the layered rocks, and the proximity to Tharsis make it a region of immense scientific value and potential safety. A future expedition might descend into its depths to set up a base for study. Tonight, the Great Canyon of Valles Marineris stretches silently across the equator of Mars. Wispy ice clouds gather along its walls in the cold morning hours. Frost dusts its floor. The patient walls hold their layers of stone. The canyon waits in the long quiet of the Martian night. Now gently, we will travel from the Great Canyon to the cold poles of Mars, where layered ice and frozen carbon dioxide form bright caps at the top and bottom of the planet. Mars has two bright polar caps, one at the North Pole and one at the South. Both caps are made of frozen water and frozen carbon dioxide, also called dry ice. The water ice is permanent, lasting throughout the year. The carbon dioxide ice is mostly seasonal, growing in winter and shrinking in summer as it sublimates back into atmospheric gas. The North Polar Cap is the larger of the two. It is about 1,000 kilometers across, roughly the size of Greenland. Most of it is made of water ice, with a thinner layer of seasonal carbon dioxide ice on top in winter. The cap is several kilometers thick at its center. Underneath the ice, the Martian surface curves gently downward into a polar basin. The South Polar Cap is smaller, about 400 kilometers across. Unlike the North, the Southern Cap has a permanent carbon dioxide ice covering, the only place on Mars where carbon dioxide ice never fully melts away. Below the carbon dioxide ice, the Southern Cap also contains substantial amounts of water ice, layered together in alternating bands. Both polar caps show beautiful spiral patterns from orbit, formed by winds carving channels into the ice over millions of years. The patterns are unique to each pole and reflect the direction of polar circulation in the Martian atmosphere. Mars Reconnaissance Orbiter and Mars Express have photographed these patterns in stunning detail. Each Martian winter, the polar caps grow substantially. Carbon dioxide gas in the atmosphere freezes directly onto the existing ice cap surface in a process called sublimation in reverse. Up to 30% of the entire Martian atmosphere can condense onto the polar caps during the coldest months. The atmospheric pressure of the planet rises and falls with the seasonal cycle of the caps. In spring, when sunlight returns to the poles, The carbon dioxide ice slowly sublimates back into atmospheric gas. The cap shrinks. The released gas thickens the atmosphere temporarily and sometimes triggers regional dust storms. The seasonal cycle repeats every Martian year, with the carbon dioxide moving back and forth between atmosphere and pole. Beneath the polar caps lie thick layers of ice and dust, deposited over hundreds of thousands or millions of years. These layered deposits hold a complete climate record of Mars going back deep into geological time. By analyzing the layers, scientists can read past changes in the Martian climate, periods when the poles were warmer, periods when they were colder, periods when dust storms were more frequent. The total amount of water ice in the polar caps of Mars is substantial. If all the polar water ice on Mars were melted, it would cover the entire planet to a depth of several meters. There is more water locked in the polar caps and in subsurface ice elsewhere on Mars than was once thought, and possibly enough to support future human settlements. The European Mars Express spacecraft used ground-penetrating radar to detect what appears to be a lake of liquid water beneath the South Polar ice cap, several kilometers down. The detection was made in 2018 and has been the subject of ongoing study. If confirmed, this subsurface lake would be the first known liquid water on Mars today and a potential habitat for microscopic life. During the long Martian winters, the polar regions experience polar night, months of complete darkness as the sun stays below the horizon. The temperatures during polar night can fall to below -120 degrees Celsius. Carbon dioxide ice grows quickly on every surface, including spacecraft and rovers that might be operating in those regions. In summer, the polar regions experience polar day, months of continuous sunlight. The sun circles low over the horizon without setting. The carbon dioxide ice sublimates rapidly. Dust storms often rise in the polar regions during this time, carried by the strong winds generated by the temperature gradient between sunlit ice and warmer surrounding surfaces. Some of the most beautiful features on Mars are the seasonal jets that emerge from the South Polar Cap in spring. As sunlight warms the underside of the carbon dioxide ice, gas builds up and bursts through the surface in geyser-like jets. These jets carry dark dust upward into the air, which then settles in spider-shaped patterns on the white ice below. The polar regions hold immense importance for future human exploration of Mars. The water ice can be melted for drinking water, electrolyzed for breathable oxygen, and combined with the carbon dioxide of the atmosphere to make rocket fuel. A human base near one of the poles would have access to nearly unlimited supplies of all these crucial resources. Both polar caps have been visited by spacecraft. The Phoenix lander reached the northern polar region in 2008 and confirmed the presence of water ice just below the surface. The Phoenix mission ended when the polar winter froze and damaged its solar panels. Future missions may attempt longer-term observations of both poles. Tonight, the polar caps of Mars sit cold and bright in the long Martian night. Frost gathers patiently on the layered ice. Dust drifts slowly across the polar plains. The carbon dioxide ice grows or shrinks according to the season, while the deep water ice rests, patiently locked in the frozen ground for billions of years. Now gently we will turn from the cold poles to the great planet-wide dust storms that can sweep across all of Mars in just a few weeks. Mars is famous for its dust storms. Small dust storms occur somewhere on the planet almost constantly. Larger storms cover whole regions for weeks. Occasionally, the largest storms grow until they engulf the entire planet, blocking the surface from view from orbit for months at a time. These global dust storms are one of the strangest weather phenomena in the solar system. Local dust storms occur frequently throughout the Martian year. Most last only a few days and cover small regions, often only a few hundred kilometers across. They are caused by surface heating that creates local pressure differences, which generates strong winds that pick up surface dust. Most are barely visible from orbit, but are clearly seen by rovers on the ground. Regional dust storms are larger, covering thousands of kilometers and lasting weeks. They often form when several local storms merge, especially during the southern summer when Mars is closest to the Sun and surface heating is most intense. Regional storms can darken the sky over wide areas, reduce solar power for rovers, and influence weather patterns around the entire planet. Global dust storms, those that cover the entire planet, happen perhaps once every 5 to 10 Martian years. The most recent global storm was in 2018 and lasted about 3 months. The largest known global storm was in 2001, when the entire surface of Mars disappeared beneath a uniform veil of red dust for over 6 weeks. Even in the worst global dust storms, the wind speeds at the Martian surface are not catastrophic. Maximum surface winds during storms reach about 100 to 150 kilometers per hour. Because the atmosphere is so thin, however, these winds carry much less force than the same wind speeds on Earth. A human in such a storm would feel a moderate breeze, not a hurricane. The dust lifted by storms can rise to surprisingly high altitudes. Larger dust storms can lift dust to altitudes of 40 or 50 kilometers above the surface, well into the upper atmosphere. The suspended dust absorbs sunlight and warms the upper atmosphere, while shading and cooling the surface below. Mars, during a major storm, becomes a strange and inverted thermal world. During the 2018 global dust storm, the Opportunity rover, which had been exploring Mars for nearly 15 years, finally lost contact with Earth. The storm reduced sunlight at its location to almost nothing, draining its solar-powered batteries. Engineers continued to send commands hoping for a response, but Opportunity never replied. The end of its mission marked the end of an era of solar-powered Mars exploration. Mars dust storms have global consequences for the planet's climate. The dust absorbs solar energy and changes the heating patterns of the atmosphere. Wind circulation shifts. Polar caps grow or shrink at different rates than usual. The seasonal cycle of carbon dioxide between atmosphere and poles is disrupted. Mars, during a global dust storm, becomes briefly a slightly different planet. Dust devils, small whirlwinds, are a different and quieter cousin of the larger storms. They form when a parcel of warm air rises rapidly from the surface and rotates as it ascends. Dust devils on Mars can be much larger than their Earth equivalents. Some reach kilometers in height. They move slowly across the surface, picking up dust and carrying it upward into the thin pink sky. Dust devils have helped Mars rovers by occasionally cleaning their solar panels. As a dust devil passes overhead, its winds can blow away accumulated dust, restoring some of the rover's solar power. This unexpected cleaning has extended several rover missions. The Spirit and Opportunity rovers, both designed for 90-day missions, lasted years, partly because of repeated dust devil cleanings. Dust devils leave dark tracks across the surface as they pass. From orbit, fresh dust devil tracks appear as dark squiggly lines on the bright dusty plains, where the whirlwind has lifted the fine reddish dust to reveal darker underlying material. Some of these track patterns are so distinct they have become recognizable signatures of particular regions of Mars. Future human explorers will need to plan carefully for Martian dust. Dust devils, while not very dangerous in terms of wind force, can carry abrasive particles that erode equipment. Larger storms can darken solar arrays for weeks. Dust accumulates on rover wheels, on solar panels, on optical instruments. The Martian environment is constantly testing whether things stay clean. The planet-wide dust storms of Mars have been a subject of fascination ever since Mariner 9 arrived to find one in progress in 1971. Scientists at the time were unable to see anything but the tops of the highest volcanoes poking through the dust. They had to wait for weeks for the storm to settle before they could see the surface. The first close look at Mars came through the slow lifting of a great dust veil. Although famous, Martian dust storms in fiction are often exaggerated. The book and film The Martian famously depicted a dust storm strong enough to topple a spacecraft. In reality, no real Martian wind has been measured strong enough to do that. The fiction was acknowledged by the author as a dramatic exaggeration, but it captured the imagination of millions of readers nonetheless. Tonight, the surface of Mars is mostly quiet. A few small dust storms swirl in scattered regions. A few dust devils trail across the plains. The thin air carries its constant haze of suspended dust. The planet sits patiently between storms, waiting for the next time when the global atmosphere will lift another vast veil of red into the sky. Now gently, we will turn to the long patient seasons of Mars, the way the planet slowly cycles through its long Martian year, with each season lasting several Earth months. Mars has seasons like Earth. The axial tilt of Mars is about 25 degrees, almost identical to Earth's 23 degrees. This means that, just as on Earth, one hemisphere is tilted toward the Sun for part of the year and away for the other part. The seasonal cycle on Mars is, in its basic geometry, very similar to ours. Each Martian season lasts about 6 Earth months, roughly twice as long as our seasons. A Martian spring stretches over 6 months, then a summer, then autumn, then winter. The total Martian year is 687 Earth days. Compared to our 4 3-month seasons, Mars's slow cycle is patient and gradual. Mars's orbit is more elliptical than Earth's, so the strength of the seasons differs between the two hemispheres. The southern hemisphere is tilted toward the Sun at perihelion, when Mars is closest to the Sun. This means the southern summer is hotter and shorter, while the northern summer is cooler and longer. The southern winter is colder, the northern winter is milder. Spring on Mars begins with the slow retreat of the polar carbon dioxide ice cap. As sunlight strengthens, the seasonal frost begins to sublimate from the edges of the cap. Bright lines of receding ice slowly move toward the pole. The atmospheric pressure of the entire planet rises as the carbon dioxide returns to gas. Spring on Mars is a quiet but dramatic awakening. Summer brings the longest days at the poles and the warmest temperatures across the planet. In the southern summer near perihelion, dust storms become more common. The longer Martian summer days allow more solar heating, more atmospheric circulation, more weather. It is during these summers that the famous global dust storms most often begin. Autumn on Mars sees temperatures begin to fall. Carbon dioxide gas in the atmosphere starts to condense onto the surface in the polar regions. The polar caps begin to expand toward the equator. The atmospheric pressure drops as more carbon dioxide moves from gas to ice. Frost begins to appear in shadowed places and at higher latitudes as the cold deepens. Winter is the most extreme Martian season. The polar caps grow until they reach into the mid-latitudes. The dark side of the planet experiences months of polar night. Temperatures in the polar regions can fall to below -125 degrees Celsius. Carbon dioxide frost can be observed across vast areas of the polar surface as direct deposition from the atmosphere. Frost on Mars looks like a thin coating of white powder on the red surface. The frost is mostly carbon dioxide ice, with smaller amounts of water ice mixed in. In some places, the frost forms intricate patterns that fade slowly as the day warms. Rovers have observed frost on rocks and pebbles in winter mornings, glittering briefly before sublimating into the air. The seasonal changes affect the entire Martian atmosphere. Pressure at any given location can vary by 30% between summer and winter as carbon dioxide moves between gas and ice. Winds shift direction, cloud patterns change, dust storm frequency rises and falls. The whole atmosphere of Mars breathes slowly with the planet's seasonal cycle. Each spring at the South Pole, jets of carbon dioxide gas burst through the receding ice. As sunlight penetrates the thinning carbon dioxide ice from above, gas builds up beneath until it explodes outward, carrying dust with it. These jets create dark spider-shaped patterns on the bright ice, captured in beautiful photographs by Mars Reconnaissance Orbiter. In the milder northern winter, the polar cap grows but does not last as long or extend as far as the southern one. Different terrain and different orbital geometry give the two hemispheres different climate cycles. The poles of Mars are similar in many ways, but also distinctly different, two halves of a planet's careful seasonal balance. Seasonal changes are also visible in the atmosphere. Water vapor sublimates from the polar caps in spring and travels through the atmosphere to the opposite hemisphere, where it freezes onto the other polar cap in autumn. This slow seasonal flow of water from one pole to the other has been mapped by orbiters. Mars's water moves slowly back and forth like a long planetary breath. Mars's axial tilt has actually changed substantially over geological time. While today the tilt is 25 degrees, in past epochs it has been as low as 10 degrees or as high as 50 degrees. These changes in tilt over millions of years dramatically affected the planet's climate, the size of the polar caps, and the distribution of frozen water across the surface. The seasons of Mars are quiet by Earth standards. There are no thunderstorms, no migrating bird flocks, no leaves turning color. There are no plant cycles, no shifting wildlife, no soft summer rain. The seasons of Mars are written in dust and ice and pressure observed only by the spacecraft we have sent. They unfold patiently and indifferently across the long Martian year. Tonight, somewhere on Mars, frost is forming in a shadowed crater. Somewhere else, dust is settling after a passing dust devil. The slow seasonal rhythm continues exactly as it has for billions of years. The polar caps are slowly growing or shrinking. The atmosphere is slowly thickening or thinning. The patient cycle goes on. Now, gently, we will leave the surface of Mars and visit the two small moons that have orbited the red planet through all of its long cosmic history. Mars has two small moons, Phobos and Deimos. The larger and inner of the two is Phobos. It is about 22 kilometers across at its longest dimension, far smaller than Earth's moon, which is more than 3,000 kilometers across. Phobos is irregular in shape, looking somewhat like a slightly squashed potato. Phobos orbits Mars at an average distance of just 6,000 kilometers, the closest moon to its parent planet in the entire solar system. It circles Mars at this very low orbit at extraordinary speed. A complete orbit takes only 7 hours and 39 minutes, faster than a Martian day. Phobos completes more than 3 orbits during a single Mars day. Because Phobos orbits Mars so quickly, from the surface of Mars it appears to rise in the west and set in the east, opposite to the direction the Sun appears to move. This unusual motion is the result of Phobos's orbital speed being faster than Mars's own rotation. Anyone standing on Mars would see Phobos crossing the sky in the wrong direction. Phobos is so close to Mars that it actually orbits below geostationary altitude. Tidal forces from Mars are pulling Phobos slowly inward. Over about 50 million years, this slow tidal decay will bring Phobos so close to Mars that it will either break apart into a ring or crash into the surface. Either way, in the deep future, Phobos will not survive. The surface of Phobos is dark gray and heavily cratered. The most prominent feature is Stickney Crater, a single crater nearly 10 kilometers across, almost half the diameter of the entire moon. The impact that formed Stickney must have nearly destroyed Phobos. Long radiating grooves spread outward from Stickney across the moon's surface, possibly fractures from that ancient impact. Phobos is so low in density that scientists believe it may be partially porous inside. The moon may contain large internal voids or be a loose pile of rubble held together by gravity. Some have speculated that Phobos could be hollowed out and turned into a future space station, since landing on a low-gravity moon is much easier than landing on Mars itself. The origin of Phobos is uncertain. The moon may be a captured asteroid from the outer asteroid belt, drawn into Mars's gravity long ago. It may be a fragment of Mars itself, knocked into orbit by an early impact. It may have formed from debris of an even larger impact in Mars's distant past. Each possibility has different implications for the moon's true nature. From the surface of Mars, Phobos appears about a third the size that Earth's moon appears from Earth. It is much closer to its planet, but also much smaller, so the two effects partially cancel out. Phobos is bright enough at night to cast faint shadows on the Martian surface and to provide some light during nighttime hours. Phobos passes between Mars and the Sun frequently, causing brief eclipses. Because Phobos is small and close, these eclipses are partial rather than total. Phobos appears as a small dark spot crossing the Sun, never completely covering it. Mars rovers have captured Phobos transits in photographs, showing the small moon's silhouette passing in front of the bright Sun. The surface gravity on Phobos is so weak that a human could easily jump into orbit around it. Walking on Phobos would not be like walking at all. Every step would be a long, slow leap. Spacecraft sent to Phobos do not really land in the conventional sense. They more closely dock with the surface, holding on against the moon's tiny pull. Phobos has been visited briefly by spacecraft. The Soviet Phobos 2 mission in 1988 came close to landing on the moon but lost contact before deploying landers. The Japanese MMX mission is currently planned to retrieve samples from Phobos and return them to Earth, helping to settle questions about the moon's origin and composition. Phobos and Stickney crater have been the subjects of much speculation. Some researchers have suggested that the long grooves extending from the crater are not impact features but rather scars from interactions with debris in Mars orbit. Others have suggested they reveal internal structure. The grooves remain only partially explained, awaiting future close observation. Phobos was named for the ancient Greek god of fear, the son of Ares, who is the Greek equivalent of the Roman Mars. The name was given by astronomer Asaph Hall, who discovered both Martian moons in 1877. Fear is an unusual choice for a moon's name, but it fit the war god theme of Mars and Phobos' small, swift, menacing motion. Tonight, Phobos races above Mars in its very low orbit, completing more than 3 trips around the planet during the long Martian day. The small moon rises in the west, crosses the pink sky in roughly 4 hours, and sets in the east. Its small dark form will pass briefly across the Sun several times before tomorrow comes. Phobos has been waiting in this orbit for billions of years. It will continue for another 50 million or so before tidal forces finally tear it apart. The patient gravitational pull of Mars is, in geological time, slowly dragging this small moon downward toward an inevitable end. But not tonight. Tonight, Phobos still races silently above the red planet. Now, gently, we will travel out to the smaller and more distant of the 2 Martian moons, Deimos, the gentle outer moon. Deimos is the smaller and more distant of Mars's 2 moons. It is just 12 kilometers across, about half the size of Phobos. Like Phobos, Deimos is irregularly shaped, resembling a smooth, lumpy potato. Its surface is dark gray and lightly cratered. Deimos is one of the smallest known moons in the solar system. Deimos orbits Mars at an average distance of about 23,000 kilometers. This is far higher than Phobos, but still very close compared to Earth's moon, which orbits at about 384,000 kilometers. From orbit, Deimos is small enough to be hard to see at first glance, often appearing as just another point of light against the cosmic dark. A single orbit of Deimos around Mars takes about 30 hours and 18 minutes, slightly longer than a Martian day. Because of this, Deimos appears to move slowly across the Martian sky in the normal direction, from east to west. Unlike Phobos, Deimos moves predictably from horizon to horizon, but very slowly. From the surface of Mars, Deimos looks like a bright star rather than a moon. It is too small to show a disk to the unaided eye. It might be one of the brighter objects in the night sky, easily mistaken for a planet at first glance. Even when it crosses the Sun in a transit, Deimos is just a tiny dark spot, far smaller than Phobos against the same solar disk. The surface of Deimos is smoother than that of Phobos. It has fewer craters and seems to be covered with a thick layer of regolith, broken rock and dust that fills in many small craters and softens the appearance of larger ones. Spacecraft photographs of Deimos show a gentle and surprisingly smooth-looking world for its small size. Like Phobos, Deimos is named for an ancient Greek god, in this case the god of dread, brother of Phobos. Both names were given by astronomer Asaph Hall when he discovered the moons in 1877, and both are appropriate to the war god theme of Mars itself. The two small moons of fear and dread orbit the planet of war. Unlike Phobos, Deimos's orbit is stable. The moon is not being pulled inward toward Mars. In fact, Deimos is slowly moving outward, gradually drifting away from the planet at a few centimeters per year due to subtle tidal effects. In the distant future, Deimos may eventually escape Mars's gravity altogether and become a small asteroid orbiting the Sun. The composition of Deimos is similar to that of Phobos. Both moons appear to be dark, carbonaceous, and similar in composition to certain types of asteroids found in the outer asteroid belt. This similarity has led to the leading theory that both Martian moons are captured asteroids, small bodies that were once orbiting the Sun and were pulled into Mars's gravity long ago. However, the orbital characteristics of Deimos make the simple captured asteroid theory difficult. Captured asteroids should have eccentric tilted orbits, but both Martian moons have nearly circular orbits in Mars's equatorial plane. This suggests they may have formed from debris of an ancient impact or undergone substantial gravitational interactions to circularize their paths. Deimos has very low gravity, even lower than Phobos. A person standing on Deimos would weigh almost nothing. An athletic person could probably jump high enough to leave the moon's surface altogether and become a small object orbiting Mars. The escape velocity from Deimos is so low that simply throwing a baseball hard could send it into orbit around the planet. Photographs of Deimos taken by Mars Reconnaissance Orbiter and Viking Orbiter show the small moon in considerable detail. The largest crater on Deimos is only about 2 kilometers across, small compared to Stickney on Phobos, but still substantial relative to Deimos's 12-kilometer size. The moon is more lightly cratered than Phobos and appears to have a different impact history. No spacecraft has yet landed on Deimos. The proposed Japanese MMX mission may visit Deimos briefly as part of its primary mission to Phobos. A direct study of Deimos would help answer questions about the origins of both Martian moons. The smallness and weak gravity of Deimos make it both easier and harder to visit, easier to leave, but trickier to land softly. From Mars's surface, the two moons together, though both small, provide some of the most distinctive sights in the Martian sky. Phobos crosses quickly from west to east. Deimos drifts slowly from east to west. Sometimes they appear together, sometimes one crosses the sun while the other shines in the night. They are silent companions in the long quiet of Mars's evenings. Deimos was the first object whose discovery used the Mariner 9 spacecraft to obtain detailed images. Photographs of Deimos as it appeared from the orbit of Mariner 9 in 1971 revealed for the first time that this tiny moon had a real and distinct surface, not just a pinpoint of reflected light. Until then, Deimos had been studied only from telescopes at Earth. Tonight, Deimos drifts slowly in its high orbit around Mars. It crosses the long Martian night, taking many hours to move from horizon to horizon. Its small dark form catches the distant sunlight as it moves through space, a small dim companion to its faster cousin Phobos. The patient outer moon keeps its own slow time. Now, gently, we will return to the surface of Mars and look at what may once have flowed there, the patient ancient waters that perhaps lapped against shores long since faded away. Mars is dry today, but it was not always so. The evidence is written across the surface in features that could only have been carved by flowing water. River channels, lake basins, ancient shorelines, and sedimentary rocks all point to a wetter Mars billions of years ago. The deep past of the planet was very different from its cold, dry present. Long, winding channels run across many regions of Mars. Some are narrow valley networks, branching like Earth river systems. Others are broad outflow channels, the floors of which were sculpted by enormous floods. Some of the channels stretch for thousands of kilometers and would have carried water comparable to Earth's largest rivers or much greater. The Curiosity rover, exploring Gale Crater, found evidence of an ancient lake that lasted for hundreds of millions of years. Fine layered sedimentary rocks deposited in the lake bottom told a story of patient water flow. The lake would have had liquid water for long enough that any life present might have had time to develop and leave traces of itself in the rocks. Some scientists believe that the northern lowlands of Mars once held an ocean. Maps of the planet show what appears to be a vast, smooth basin covering nearly a third of the surface, a basin that could have held an ocean kilometers deep. Possible shoreline features have been identified along its edges. The northern ocean of Mars, if it existed, would have been one of the largest bodies of water in the inner solar system. River deltas have been found in many places on Mars. Where ancient rivers flowed into lakes, they deposited fan-shaped sediment deltas exactly like the deltas of Earth rivers. Several of these deltas have been examined in detail by orbital cameras and rovers. They appear to have been formed over timescales of thousands to millions of years. The Perseverance rover landed in Jezero crater in 2021, in part because Jezero contains a beautiful ancient river delta. The rover is currently exploring this delta, collecting rock samples from layers laid down when an ancient river carried sediments into an ancient lake. The samples are being stored on the surface for a future mission to retrieve and return to Earth. Mars's water did not vanish overnight. Over billions of years, the planet's atmosphere thinned and its temperature fell. Liquid water on the surface gradually retreated, then disappeared. Some of it escaped into space as water vapor that was broken apart by sunlight. Some of it froze into the polar caps and the subsurface ice. Some may still lie hidden in pockets deep underground. The first clear evidence of past water on Mars came from the Viking orbiters in the 1970s. The orbiters photographed channel networks and crater wall gullies that strongly resembled features on Earth caused by flowing water. The evidence has only grown stronger in the decades since. Multiple rovers and orbiters have confirmed an extensive history of liquid water on Mars. Some channels on Mars seem to have been carved by single catastrophic floods rather than long sustained rivers. The outflow channels of the chaos terrain region near Valles Marineris show evidence of releases of huge volumes of water in very short periods, perhaps weeks. The flow rates were enormous, perhaps 1,000 times greater than the largest Earth flood. The mineral evidence for past water is also strong. Rocks examined by rovers contain clay minerals, sulfates, and other minerals that can only form in the presence of liquid water. Some of these mineral assemblages are similar to those found in environments on Earth that support life, providing one of the strongest hints that ancient Mars may have been habitable. Recurring slope lineae are dark streaks that appear on certain Martian hillsides during warmer months and fade during colder ones. They were once thought to be evidence of small flows of briny water seeping from the subsurface. More recent analysis suggests they may instead be dry granular flows of fine dust. The mystery of these slope lineae continues to be studied. Subsurface ice on Mars is widespread. Radar data from orbiters shows that buried glaciers exist in many regions of mid-latitude Mars. These glaciers may be several kilometers thick in places, covered by a thin layer of rock and dust. They are largely water ice preserved through millions of years of cold climate. The total amount of subsurface water ice on Mars is enormous. If Mars once had as much surface water as the evidence suggests, the planet was likely a much friendlier place for life. Rivers flowed, lakes filled, an ocean may have lapped against shorelines. The atmosphere was probably thicker and the temperature warmer for a period of perhaps 1 billion years in Mars's youth. The planet may have looked surprisingly Earth-like. Whether life ever arose on ancient Mars is one of the great open questions in science. We do not know yet. We are looking. Mars rovers are collecting samples in the very rocks that might preserve the chemical or fossil traces of ancient Martian microorganisms. Future missions will bring these samples back to Earth for detailed study. The answer may come within our lifetimes. Tonight, the dry plains of Mars hold their patient memory of water. The riverbeds wait, dry and red. The delta sediments preserve the marks of long-ago currents. The polar ice quietly holds the planet's remaining water. The thin air carries traces of the lost ocean as drifting water vapor between the poles. The slow story continues. Now, gently, we will turn to one of the deepest questions humanity has ever asked. Was there once life on Mars? And could there still be life there today, hidden in some warm, wet corner of this otherwise dry world? The question of whether life exists or once existed on Mars is one of the oldest and deepest questions in human science. For a long time, scientists believed Mars might support life. Telescope observations in the 1800s seemed to show seasonal changes in dark patches on the surface. perhaps vegetation. The idea of life on Mars was so accepted that the canals controversy of that era could even be taken seriously. Modern spacecraft have shown that Mars has no large-scale vegetation, no surface oceans, no atmosphere capable of supporting complex life as we know it on Earth. But this does not rule out simpler forms, single-celled life, perhaps hidden in subsurface water pockets or surviving in dormant states in the soil. The search for microscopic life on Mars continues with each new mission. Past Mars was likely much more habitable than present Mars. 3 to 4 billion years ago, the planet had rivers, lakes, possibly an ocean, a thicker atmosphere, and possibly a stronger magnetic field. The conditions for life as we understand it were probably much more favorable then. If life arose on Mars, it would likely have done so during this early period. The Viking missions in 1976 conducted the first direct experiments designed to detect microbial life on Mars. 2 landers tested Martian soil samples for biological activity. The results were complex and have been debated ever since. Most scientists today consider the Viking results inconclusive, but some still argue that the data could be interpreted as detecting life. Since Viking, every subsequent Mars mission has searched for indirect signs of life. The strategy has shifted from looking for living organisms to looking for traces of past life, biosignatures. These could be specific chemicals only made by life, microscopic fossils in ancient rocks, or unusual mineral patterns that suggest biological activity. Methane has been detected in the Martian atmosphere by both rovers and orbiters. On Earth, most methane is produced by living organisms, particularly by methanogens, certain types of bacteria. The Martian methane fluctuates in mysterious ways with seasonal variations and unexplained spikes. The source of this methane remains unknown. Geological processes can produce methane, but so can life. The Curiosity rover has found organic molecules in Martian rocks. Organic molecules are carbon-based compounds, the building blocks of all known life. While organic molecules can form by purely non-biological processes, their presence on Mars confirms that the planet has the basic chemical ingredients needed for life. The detection of organics raised hopes that more direct evidence might one day be found. The Perseverance rover is currently collecting samples from Jezero crater, where an ancient lake and river delta preserve the most promising habitat for ancient microbial life found on Mars so far. The samples are being carefully cached on the surface for retrieval by a future Mars sample return mission. The samples may take decades to bring back to Earth, where they can be analyzed in detail. The detection of liquid water beneath the South Polar ice cap, if confirmed, opens up another possibility. Earth's deep underground waters host thriving microbial ecosystems. A subsurface lake on Mars could potentially do the same. Future missions may try to drill down to such water reservoirs, though doing so without contaminating them with Earth microbes will be a significant challenge. If life does exist on Mars or once did, it could share a common origin with Earth life. The 2 planets exchange material as meteorites. Rocks ejected from one planet's surface by impacts can drift through space and eventually fall on the other. Some Martian meteorites are already in our collections on Earth. Life could theoretically have been transferred between the 2 planets in either direction. The discovery of even very simple life on Mars would be one of the most important scientific discoveries in human history. It would mean that life is not unique to Earth and that biology can arise in different environments. It would suggest that life may be common throughout the universe, that our own existence is not a freak occurrence but part of a much larger cosmic pattern. Even if no life is ever found on Mars, the negative result would be scientifically important. It would tell us that habitable conditions are not enough on their own, that something else may be needed for life to arise. It would refine our understanding of how rare or common life is in the universe. Whether the answer is yes or no, the question is worth asking. Some scientists have proposed that we should be cautious about contaminating Mars with Earth life. Spacecraft are carefully sterilized before launch to prevent Earth microbes from accidentally colonizing Mars. The protocols are not perfect, but they reflect a real concern. The first life found on Mars should not turn out to be life we accidentally brought ourselves. Some of the most intriguing places to look for life on Mars are not on the surface, but deep underground. The deep biosphere of Earth, life living within the rock kilometers below the surface, has revealed an unexpected richness of life in environments once thought sterile. Mars's deep subsurface may host similar ecosystems, protected from radiation and cold by overlying rock. Tonight, perhaps somewhere on Mars, microscopic life rests dormant in cold rock or briny ice. Perhaps it is gently active in some warm subsurface pocket we have not yet found. Perhaps no life exists there at all. The question waits patiently for an answer. The red planet keeps its secrets quietly across the long cosmic time. Now gently, we will turn from this great open question to the history of human exploration of Mars, the long, careful effort by which our species has slowly come to know our smaller neighbor. The exploration of Mars by spacecraft began in 1965 with Mariner 4. This small NASA probe flew past Mars at a distance of about 10,000 kilometers, sending back just 21 photographs of the surface. The images were grainy and showed mostly craters. For the first time in history, humans saw Mars not as a distant point of light, but as a real world with its own surface features. The Mariner 4 images were a disappointment to those who had hoped for evidence of canals or other signs of advanced life. Mars looked like the Moon, heavily cratered, dry, and apparently lifeless. The vegetation theories that had survived since the 1800s finally died. Mars became, in the public imagination, a small dead world. Mariner 6 and Mariner 7 followed in 1969, flying past Mars and sending back more detailed photographs. They captured the polar caps and various surface features. They could not yet detect the great volcanoes of Tharsis or the canyons of Valles Marineris because they only photographed limited regions during their flybys. Mars was still being seen in disconnected glimpses. Mariner 9 arrived at Mars in 1971 and entered orbit around the planet. It was the first spacecraft ever to orbit another planet. Mariner 9 arrived in the middle of an enormous global dust storm that obscured the entire surface. The spacecraft waited patiently in orbit for the storm to settle. Eventually, when the dust began to clear, Mariner 9 revealed Mars as no one had ever seen it before. Mariner 9 discovered Olympus Mons. It discovered Valles Marineris. It discovered the channels and outflow features that hinted at ancient water. It revealed the polar caps in detail. It photographed Phobos and Deimos. Mariner 9 produced the first global maps of Mars and transformed our understanding of the planet from a small dead world to a complex geological wonderland. The Viking missions in 1976 were the next great step. Two spacecraft, Viking 1 and Viking 2, each consisted of an orbiter and a lander. The orbiters mapped the surface in unprecedented detail. The landers were the first probes ever to touch down softly on Mars and operate on its surface. For the first time, humans saw the Martian landscape from ground level. The Viking landers each carried biological experiments designed to test for life. Soil samples were scooped up and analyzed in small instruments inside the spacecraft. The results were mixed. One experiment produced strange responses that might have been biological but might also have been chemical reactions. Another found no organic molecules at all. The Viking biology results remain debated decades later. The Viking landers operated for years on the Martian surface. Viking 1 sent its last signal in 1982, 6 years after landing. Viking 2 had stopped sending in 1980. Their long missions returned thousands of photographs of the Martian landscape, weather data, soil chemistry, and seismic observations. They established the foundation on which all later Mars exploration was built. After the Viking era, Mars exploration entered a long, quieter phase. Throughout the 1980s and into the 1990s, very few missions were sent. Soviet attempts mostly failed. American missions were planned but canceled. The Mars Observer mission was lost just before reaching orbit in 1993. The exploration of Mars seemed to have stalled. The renaissance of Mars exploration began in 1996 with Mars Pathfinder. This NASA mission carried the first successful Mars rover Sojourner, a small wheeled robot the size of a microwave oven. Sojourner operated for about 3 months, traveling slowly across the surface and analyzing nearby rocks. It captured the world's imagination and proved that rovers could work on Mars. Mars Global Surveyor arrived in 1997 and began a long period of detailed orbital mapping. The mission lasted nearly 10 years and produced extraordinary global maps of the Martian topography, gravity field, and magnetic anomalies. The Mars Orbiter camera aboard Global Surveyor revealed the surface at higher resolution than ever before, finding new features that had been missed by Viking's older cameras. Mars Odyssey arrived in 2001 and is still operating today. It is the longest-serving Mars mission with more than 2 decades of continuous data collection. Odyssey carries instruments to study the planet's surface composition, mineralogy, and subsurface water. The mission also serves as a communications relay for surface rovers. Mars Express, the first European spacecraft to orbit Mars, arrived in 2003. It has produced beautiful 3-dimensional maps of the Martian surface and made the first detection of methane in the atmosphere. Mars Express used its ground-penetrating radar to find the possible subsurface lake beneath the South Polar ice cap, one of its most exciting recent discoveries. Each of these early missions added to our growing understanding of Mars. Together, they transformed the planet from a poorly known world into one of the best-studied planetary bodies in the solar system. The questions they raised about water, climate, and habitability set the stage for the next great wave of exploration, the era of large surface rovers. Tonight, several of these older spacecraft still orbit Mars or operate on its surface. They have become part of the patient infrastructure of human presence at Mars. We watch the red planet now with eyes that span decades and continents, a slowly assembled understanding written across the cosmic dark by hundreds of careful patient scientists and engineers. Now, gently, we will look at the great rovers of the modern era: Spirit, Opportunity, Curiosity, and Perseverance, the wheeled scientific explorers that have driven across the red surface of Mars itself. The modern era of Mars exploration is dominated by large surface rovers. These are wheeled robotic vehicles, larger than the small Sojourner rover, capable of traveling many kilometers across the Martian surface. They carry sophisticated scientific instruments, cameras, and drills. They can spend years exploring Mars, returning thousands of photographs and rock analyses to scientists on Earth. The Spirit and Opportunity rovers landed in 2004 on opposite sides of the planet. Each was designed for a 90-day mission. Each lasted years. Spirit operated until 2010, 6 years past its design lifetime. Opportunity operated until 2018, almost 15 years, by far the longest-running surface mission on Mars or anywhere else beyond Earth. Spirit explored Gusev Crater, a region with possible ancient water features. The rover found evidence of past water through chemistry and mineralogy. In 2009, Spirit became permanently stuck in soft soil and could no longer move. It continued operating as a stationary platform for another year before its mission ended. The Spirit's final resting place became a kind of permanent monument on Mars. Opportunity explored Meridiani Planum on the opposite side of Mars. The rover found extensive evidence of past water, including small spherical concretions of hematite called blueberries that form in water environments. Opportunity traveled over 45 kilometers across the surface, the longest distance any rover has ever traveled on another world. Its long journey ended only with the great 2018 dust storm. Curiosity landed in Gale Crater in 2012. It is a much larger rover, the size of a small car, and carries far more capable scientific instruments. Curiosity is nuclear-powered, allowing it to operate through dust storms and through the long Martian nights. It has now been driving and studying Mars for more than a decade and is still in good health. Curiosity's mission is to look at past habitability. Whether ancient Mars could have supported microbial life, it has answered that question affirmatively. The rocks and minerals it has examined in Gale Crater show that the area once held a long-lasting freshwater lake with all the chemical ingredients needed for life. Whether life actually arose there remains unknown, but the environment was suitable. Curiosity has slowly climbed the central peak of Gale Crater, Mount Sharp, examining layers of rock that record millions of years of Martian climate change. Each layer represents a different chapter of the crater's history. The rover's slow, patient ascent has been one of the great geological expeditions ever undertaken, a vertical drive through deep time. Perseverance landed in Jezero Crater in 2021. Similar in size and design to Curiosity, Perseverance has different scientific goals. It is searching directly for biosignatures of ancient life and caching rock samples for future return to Earth. The rover landed in Jezero crater specifically because of its ancient river delta, one of the most likely places to find preserved evidence of Martian life. Perseverance also carries the first helicopter ever flown on another world, Ingenuity. Originally planned as a brief technology demonstration of just 5 flights, Ingenuity vastly exceeded its goals. It flew over 70 times across Mars before its final flight in early 2024. Ingenuity demonstrated that aerial vehicles can operate in the thin Martian atmosphere, opening a new mode of Mars exploration. Perseverance is collecting rock samples in small cylindrical tubes and caching them at strategic locations on the Martian surface. A future Mars sample return mission, currently in planning, will retrieve these tubes and bring them back to Earth, the first samples ever returned from Mars. The samples could revolutionize our understanding of the planet and possibly answer the question of whether life ever existed there. Each rover has had a distinct personality in the public imagination. Spirit was the brave climber, struggling against odds to reach the top of a hill. Opportunity was the patient long-distance traveler going farther than any vehicle on any world. Curiosity is the careful scientist, examining each rock in detail. Perseverance is the ambitious sample collector, gathering pieces of Mars for our eventual study. The rovers have also become symbols of human ingenuity and persistence. Each one was designed and built by thousands of people on Earth, then transported across hundreds of millions of kilometers of space and successfully landed on another world. Each one operates as a remote extension of human curiosity, sending back what it sees to scientists who guide its journey from afar. The cameras on these rovers have given humanity our most detailed views of an alien landscape. Tens of thousands of photographs have been returned, showing red dust, rocky plains, distant hills, and the soft pink Martian sky. These images have entered the visual vocabulary of our species. Mars is no longer a distant abstract concept, but a concrete place with familiar landmarks. Future Mars rovers and landers are being planned around the world. The European Rosalind Franklin rover is designed to drill deep into the Martian subsurface in search of preserved biosignatures. The Chinese Tianwen-3 mission is planned to attempt sample return. Multiple commercial and government missions are in various stages of development. The pace of Mars exploration has never been faster. Tonight, curiosity and perseverance both rest on the Martian surface in the long cosmic night. They are conserving power for tomorrow, when they will continue their slow, patient work. Their wheels are dusty. Their cameras point toward the cold, dark sky filled with unfamiliar stars. They have become quiet inhabitants of Mars in their own way. Now, gently, we will leave the rovers and turn to the long story of Mars in human history, the way our species has imagined and named and dreamed about the red planet across all of recorded time. Mars has been known to humans for as long as humans have looked at the night sky. Because of its red color, the planet has been associated with blood, fire, and war in cultures around the world. Long before telescopes, long before our species understood that Mars is a planet, People watched the slow red light tracing its way among the stars and wove stories around its appearance. The ancient Egyptians called Mars Her-di-Sher, the Red One. They observed its retrograde motion when Mars appears to move backward against the stars for several months at a time, and incorporated this strange motion into their astronomical understanding. They tracked it carefully across their long calendar of years and used it to mark certain rituals and observations. The ancient Babylonians and Sumerians named Mars Nergal after their god of war and pestilence. To them, the red planet was an unfortunate omen, its appearance in the sky associated with conflict and disease. They carefully recorded its positions on cuneiform tablets that survive to this day, providing some of the oldest astronomical records ever made. The ancient Greeks called the red planet Ares after their god of war. The Romans, who adopted much of Greek mythology, kept the war god association and called the planet Mars, the name we still use. The two small moons discovered much later, Phobos and Deimos, were named for the sons of Ares, the personifications of fear and dread who accompanied their father into battle. The Chinese called Mars the fire star, and similarly associated it with conflict, change, and impermanence. Like other ancient observers, Chinese astronomers carefully tracked the planet's position and used its motion to make astrological predictions. Mars retains a place in traditional East Asian astrology as a planet of energy and unrest. Hindu astronomy named Mars Mangala, derived from a Sanskrit name for the planet. In Hindu astrology, Mangala represents energy, vitality, and aggression, qualities similar to those associated with Mars in other traditions. The day Tuesday is named for Mangala in Hindu tradition, just as Tuesday is named for the war god Tob in English and many other Indo-European languages. The first telescopic observations of Mars in the 1600s revealed a small red disk with vague dark and light markings. Astronomers including Christian Huygens and Giovanni Cassini made careful drawings and used the markings to measure Mars's rotation period. They correctly determined that a Mars day is approximately equal to an Earth day, an extraordinary insight for the time. In the 1870s, the Italian astronomer Giovanni Schiaparelli reported seeing fine straight features on Mars that he called canali, Italian for channels. The word was mistranslated into English as canals, suggesting artificial waterways constructed by intelligent beings. The Mars Canals controversy raged for decades and inspired countless science fiction stories about Martian civilizations. Percival Lowell, an American astronomer, became the most famous champion of the canal theory in the late 1800s and early 1900s. He built a private observatory in Arizona dedicated to studying Mars and wrote several books arguing that the canals were the work of an advanced Martian civilization that built them to bring water from the polar caps to the equator. His ideas captured the public imagination. The canal theory inspired H.G. Wells to write The War of the Worlds in 1897, one of the founding works of science fiction. Wells imagined intelligent Martians invading Earth in machines that wreaked havoc on human civilization. The novel was wildly popular and shaped expectations about Mars for generations. The famous radio adaptation in 1938 reportedly caused panic among listeners who thought it was a real invasion. Many other classic science fiction works imagined life on Mars. Edgar Rice Burroughs wrote a long series of adventure novels set on a Mars he called Barsoom, populated with various Martian races and dramatic civilizations. Ray Bradbury's The Martian Chronicles imagined a slow, gentle Martian world and humanity's complex first encounters with its inhabitants. Mars became a place where science fiction could project hopes and fears about ourselves. By the mid-20th century, the Mars of fiction had largely diverged from the Mars of science. As telescopes improved, no canals could be confirmed. The bright and dark patches turned out to be dust and frost. The signs of vegetation faded. When Mariner 4 returned its first photographs in 1965, the Mars of imagination was largely demolished. The Mars of reality emerged as something quieter and stranger. Mars in modern fiction has become more grounded but no less rich. Kim Stanley Robinson's Mars trilogy imagined a careful, realistic colonization of Mars over centuries. Andy Weir's The Martian told a tense survival story rooted in real engineering. Even as the romance of Martian civilizations faded, the romance of human exploration of Mars has grown to take its place in our cultural imagination. Mars continues to occupy a unique place in human culture. It is real enough that we send robots to explore it, but distant and strange enough to support endless imagination. It is the planet we have studied most intensely beyond our own, and the planet most likely to one day host human visitors. The cultural meaning of Mars has shifted from gods to fiction to a real destination, but it has never become uninteresting. Tonight, Mars shines as a bright red point of light in the sky above someone, somewhere on Earth. Children point up at it. Old astronomers track it from observatories. Spacecraft above it send back data. The same planet has been watched and named and dreamed about for tens of thousands of years. Its red light continues to fall gently on humanity, exactly as it has fallen since we first looked up. Now gently, we will look toward the future of Mars exploration, the future of possible human visits, the future of the red planet as our species continues to dream about reaching out to it. Human exploration of Mars has been a dream since long before space travel was possible. As soon as it was clear that Mars was a real world with its own surface, generations of scientists, engineers, and writers began thinking seriously about how humans might one day go there. The question has shifted from whether to when and how, though those questions remain difficult. A human Mars mission would be enormously more difficult than any previous space expedition. The distance from Earth to Mars is hundreds of times greater than the distance from Earth to the Moon. The journey takes about 6 to 9 months one way, depending on planetary positions. Astronauts would need to live in a small spacecraft for that long, exposed to radiation and isolation. Once on Mars, the astronauts would need to survive in a harsh environment. The cold would require heated habitats. The thin atmosphere would require sealed living quarters and oxygen tanks. The radiation would require shielding by either rock walls or thick water-filled barriers. Every aspect of human survival would require complex engineering to make Martian environments livable. Resources on Mars could supply some of what astronauts need. Water, ice in the subsurface, and polar caps can be melted for drinking water and electrolyzed for oxygen. The carbon dioxide of the atmosphere can be combined with hydrogen to produce methane fuel for return journeys. Iron, silicon, and other elements in the soil could provide construction materials. The Martian environment, though harsh, is not entirely hostile. Many proposals exist for how human Mars missions might be staged. Some plans involve sending supplies in advance, robotically, so that astronauts arrive at a prepared site. Others involve a single grand mission that carries everything needed. Still others propose international cooperation among multiple nations to share the enormous cost. The exact path forward is still being debated and planned. NASA has long planned to send humans to Mars, with target dates that have repeatedly shifted decades into the future. The Artemis program currently focuses on returning humans to the Moon and using the Moon as a stepping stone for Mars missions. Private companies, particularly SpaceX, have announced ambitious plans for Mars colonization that may move faster than government programs. The first humans to land on Mars will face risks unlike any previously encountered. They will be the most isolated humans in history, far from any rescue. Communication with Earth will be delayed by minutes due to the speed of light. Medical emergencies will need to be handled by the crew alone. Psychological challenges of isolation and confinement will be substantial. They will be true pioneers. Some have proposed that the first Mars missions should be one-way trips. The cost of bringing astronauts back is enormous. A one-way colonization mission would be cheaper and could establish a permanent human presence on Mars more quickly. The idea is controversial. Some see it as a noble sacrifice, others as an irresponsible gamble. It remains one of the more debated possibilities for human Mars exploration. If a long-term human presence is established on Mars, the planet could slowly be transformed by its new inhabitants. The concept of terraforming, engineering Mars to be more Earth-like over centuries or millennia, has been seriously discussed. Thickening the atmosphere, warming the planet, melting the polar caps to release water could in principle create a more habitable Mars over very long timescales. Terraforming Mars would be the largest engineering project ever attempted by humans. Estimates of how long it might take vary enormously from centuries to millions of years. Many scientists doubt it can be done at all given Mars's small size and weak gravity. Others believe it is theoretically possible, but practically beyond reach for the foreseeable future. The dream persists nonetheless. Ethical questions about human Mars exploration are increasingly being raised. If there is life on Mars, even microscopic life, should we go there at all? Would we contaminate it with Earth life? Would we destroy a unique alien ecosystem? Some scientists have argued for a careful precautionary approach with detailed biological surveys before any human landings. These are real questions that will need answers. Even before humans arrive, advances in robotic exploration continue. New rovers will be sent. Sample return missions will bring Martian rocks to Earth. Aerial vehicles will explore the atmosphere. Subsurface drilling missions will probe for buried water and life. The robotic exploration of Mars will only intensify over the coming decades, preparing the way for whatever follows. The first human footprints on Mars will mark a transition for our species. We will become a species that lives on more than one world. The cultural and philosophical significance of that moment will be enormous, comparable to or greater than the first moon landing. Whoever takes that first step will be remembered for as long as our civilization endures. Whether humans will visit Mars in this century or the next, or eventually live there permanently, remains uncertain. What seems certain is that the dream continues. Each new generation of children grows up with Mars present in their imaginations, in books, in films, in actual rovers exploring its surface. The red planet has become not just a place but a horizon, drawing our species slowly outward. Tonight, Mars waits in the cold cosmic dark, exactly as it has waited for 4.5 billion years. The dust still drifts, the polar caps still expand and shrink. Phobos still races above. Whether human boots will eventually press into the red sand, or whether Mars will remain forever a robotic destination, the patient planet continues its quiet journey through space. Now, gently, we will bring our journey through Mars to a soft close, returning slowly to the quiet of sleep. Thank you for being here through this long, quiet journey. If sleep is finding you, then we have done what we set out to do tonight. Subscribing keeps these visits coming week after week, always through the slow places of the quiet world of Mars and its red plains, always at this unhurried pace. Good night from the Circadian Institute. Sleep deeply, sleep well. Mars is still rotating quietly through the cold cosmic night tonight. The dust is still drifting gently across its iron-red plains. The polar caps are still slowly turning beneath their seasonal frosts, and Phobos and Deimos are still tracing their long patient orbits around the red planet exactly as they have for billions of years. And tomorrow, when you wake, all of this will still be true. Good night. And with that, we bring tonight's quiet journey through the world of Mars to a soft close. The dust is still drifting, the polar caps are still growing or shrinking, Phobos and Deimos are still tracing their long, patient orbits. They will all continue without us. Sleep softly tonight.